We know how to identify slope from an equation. We know how to identify y-intercept from an equation. And we know why they call it slope-intercept form. Because just from looking at it in slope-intercept form, we can tell what the slope is and what the y-intercept is. Good? Okay. So our application problems today are going to have to do with one of these two things changing. So let me give you an example of this. So if you earn $8 an hour for babysitting, $8 per hour, and somebody gives you a $10 weekly allowance for gas money. So maybe once a week you get the $10, okay? Or once a month, whatever. But then on top of that $10, you get $8 an hour. So let's just change that, so making that match. Then your friend gets paid $12 an hour, but they also get that same $10 bonus. So everything's the same except they make $4 an hour more than you. Kind of stinks, right? Okay? So what I'm trying to get you to think about is lines on a graph, right? Okay? So right now, if I were to ask you to graph those two lines on the same coordinate plane, could you kind of visualize what they would look like? Would they be parallel to each other? No. Very good. Very quickly, you didn't hesitate. You know that they're not parallel to each other because the rate of change is different. So step one, would you be able to write an equation from this, knowing what your rate of change is and what your beginning value is? So what would my equation be for this one? Y equals 8x plus 10, which would make this one y equals 12x plus 10. So something's the same, it's just not slope, right? So the slope isn't the same, but the y-intercept is. So if I had a piece of graph paper like this, would quadrant 1 be sufficient enough for me to plot this? Yeah. Because do I need to go into negative territory for anything? Okay, so the first thing you need to think about is this. What did I say is almost always goes on your x-axis? Time, right? Because usually, not usually, all the time you're independent. So maybe you can just do a quick little, I have an official one. You can just sketch one maybe in your notes real quick. So your independent variable goes here, which is time. And you might even want to say, to specify your unit of time. There are lots of different ones, seconds, minutes, hours, days, weeks. So we're going by hour. Your y is your dependent and is usually money. Let's think about this. Does time depend on money or money depends on time? Your money depends on your time because how much you make depends on how many hours you work. Agreed? Okay? So the money you make depends on the time, and so that's on your dependent variable axis, which is the y. Okay? So if I were to plot both of these lines, where would I start? At 10. So would I be in the same spot for both of them? Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? And I'm not going to get really precise after this. Where would I go? And I don't really care about the actual slope right now. For one of them, if my graph was big enough, I'd go up 8 and over 1. For the other one, I'd go up 12 and over 1. So here's what you have somewhere on your paper, right? You have something that looks like this, and then maybe something that looks like this, correct? Now I want to ask you, which line goes with which equation? One of them's steeper. So Dominic, go ahead. Yes. So you learned from the last assessment we took. Remember that very last question I asked about ski slopes and I said, which one's the hardest? And then at the very bottom you said, the bigger the number, the steeper the slope, right? $12 is more than $8. So this is the y equals 12x plus 10 line. And this is the y equals 8x plus 10 line. Agreed? That should be nothing new to you. Okay, so I'm trying to get you to kind of see if this graph makes sense. All right? So now let's take a look at an example in the book. So the book says that you are at the mall, and there's 2 floors in the mall. And you know that there's the escalator or the stairs. Okay, so let's say there's stairs in the mall. Okay? So I want you to take a look at, so go ahead and put escalator, stairs. If you keep and by the way, there's a difference of 28 feet from the first floor to the second floor. That is your vertical distance that you need to travel. So the floor of floor 1 and the floor of floor 2, where your feet would be, are 28 feet apart. If you take the escalator, you can walk or you can travel at a rate of 2 feet per minute. Okay? Per second. Sorry, that would be a really slow walker. People would be like pushing you up. They're like, come on. So we're going to change that to seconds. Yeah. That would be taking a nap on the escalator. All right. If you take the stairs and you're walking at the same rate, you could travel 1.75 feet per second. Okay? So, I have all the information I need to set up this double graph. Okay? Now, here's what I'm asking you though. You have to travel, so we're going to use, I'm going to ask you to write an equation using d in distance. Write an equation using d for distance. Now be careful. This next word is a game changer. For the distance that you have left to travel. Okay? So the distance that you have left to travel. And then we're going to use, it says use T for time. I kind of like using the, use S for seconds. It just makes it a little easier to interpret once you are, giving your conclusion. So I want you to write an equation for the escalator. I want you to write an equation for the stairs. So let's think about this. So they're both going to start out with distance. Your total distance that you have left, where before your foot takes off for that first step, whether it's the escalator or the stairs, how many feet do you have left to travel? 28. So here's what some people like to do. They like to put the starting value first. Usually, where do we see it? At the end. I'll show you both ways. Now, every second that goes by, that distance that I have to go until I get to that second floor is doing what? Increasing or decreasing? It's decreasing. So I am decreasing this by 2 feet per second. Do you agree with that? Okay? Because look, let's say I'm traveling for 1 second. I put 1 in for seconds. Now I'm 26 feet distance left. 2 seconds. Now I'm 24 feet left. Do you understand? So then what would you put here for your stairs? Minus. Yep. All right. If that bothers you, because in a way it kind of bothers me a little bit, what do you think I'm going to do? Anybody like it that way instead? With that y-intercept, you put it however you want. You can write it both ways, but just know when you're working with your problems, you can put it whichever way you want. I'm so used to my beginning value being at the end there. Works for me. If that works for you, that maybe is more logical. I don't care. Okay. So now I need to start to think about a couple things. The first question is, how long will it take you to get to the second floor if you take the stairs? How long will it take you if you take the escalator? And how much time will you save? Okay? So which one's going to get us there faster? The escalator. Why? Because I'm covering more distance per feet or per second, right? Okay? The question is, how much quicker will I get there than my friend? I know we've all done this. You go on the elevator and I'll go on the stairs. I'll meet you in this department, right? We've all done that when your parents drop you off at the mall, right? And then old people get mad at you for running up and down. So how could I figure that out? What would I do? What's your instinct to do? I want you to think about this. This right here, bless you, this goes back to intercepts. So I want you to write a big ordered pair right in the middle. And that would be, D is going to be your, actually time is seconds. And this is your distance, right? So let's make this ordered pair. 0 seconds, what goes there? Anyone? 28, right? Because 0 seconds means I haven't said go yet. The bottoms of my shoes are still on floor 1. I haven't stepped onto the escalator yet. I am still 28 feet away from my destination of floor 2. Do you understand what that ordered pair means? Okay? So now I need to figure out the ordered pair for not when my seconds is 0, but for when what is 0? My distance from my destination is 0. Hey, distance from destination equals 0 is a fancy way of saying I'm there. Agree? How far until you get where you're supposed to be? 0. Oh, it means I'm there? Yes. So what do you have to do and where? Well, how can you use these equations and 0? You put 0 where? In for D, right? So do that. Say, well, when my distance is 0 and I traveled 2 feet per second, here what would it be? When my distance is 0 and I traveled 1.75 feet per second, here what would it be? So you have to solve this baby two-step equation that I know you know how to do by subtracting. It doesn't matter what you do. It doesn't matter what side it's on. If you chose to subtract or add the that's fine too. So you're going to have negative 28 equals negative 2s, 14 seconds. So when my distance is 0, meaning I'm already there, how long did it take me? 14 seconds. Now let's do it again. And yes, you can use a calculator for this. And when I divide, yep, I get what? Yep. So now, can I ask you the question again? How long will it take on the stairs? 16 seconds. How long would it take on the escalator? 14. How much time do you save by taking the escalator? 2 seconds. Whoa, every second matters, right? The final piece of all of this is, what does it look like on a graph? Sketch what you think it will look like on that graph. Labels and everything. Get fancy. This is your time in seconds. This is your distance left till you get to your destination. You always want to make sure you divvy up that axis kind of evenly. Make sure it's not too cramped. I went by 5s, but I chose to just label by 10s. Could I have put a 5 into 15? Sure. Okay. Where are they both starting? Up here, please. Okay. And if the graph is the last thing you do, I kind of need it to be the last thing I do because I kind of need these two numbers to do my graph, don't I? Okay. So look up here. I need to go up to 16, so I'm just going to go by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18. So 4, 8, 12, 16. This is a good spread of data. I'm going to have one of my pieces of data end at 14 seconds. And then the other one ends at 16 seconds. So I'm going to connect this one with this one. And then this one with this one. And that's what your graph looks like. Okay? So, this point here, 0, 28 means you were 28 feet above, and then this 12, 0, I'm sorry, not 12, 14, 0, and 16, 0 means this was the escalator, this was the stairs, okay? Now, let me give this to you. Could you work backwards from this? What if I didn't give you any of this stuff? What if I just said, hey, tell me a little bit about this graph? Could you interpret that? Could you say, well, you have to start by looking at your axes and what they mean. Oh, this is seconds, this is distance left. You're starting at the same point, but one of your methods of what you're choosing is going a little bit faster. It's not a whole lot faster, right? It took you 14 seconds to get there. This is a little steeper, so the slope is higher, right? So does that make sense? Okay, let's try another one. When you go to print a document, okay, and this will be the last thing we do. So when you go to print a document, you had typed an 18-page paper. I know, when you get to college, that's nothing. So you have an 18-page paper, you are done, you are ready to print. There's 2 options of printing in the library. There's something called the laser printer, and then there's something called an inkjet. It's kind of an old one. Okay, laser printer is a little bit faster. You can print 6 pages per minute on the laser printer, or you can print 4.5 pages per minute on the inkjet. It's a little older. So laser's a little newer technology, right? Okay. You have all the information you need to be able to walk through that same process as we did before. Instead of starting at 28 feet vertical distance, how many pages do I have left to print? 18. What is that page total decreasing by for a laser? 6. And it's decreasing, right? So if we let P equal the number of pages left to print, right? And we're going to let M equal the number of minutes that it's been printing for, write me an equation for each. And right now will be your test to see which way you like it better. Do you put that 18 at the end or at the beginning? Totally up to you. So go ahead and see if you can come up with that equation on your own. I'm kind of traditional. I like the -6. See, that's what you got to remember. If you're going to put that slope first, I even had to think about it. So maybe it's funny because maybe my first instinct was to write the 18 because that's what I started to do. But I was fighting against it. And then it's decreasing by 4.5 per minute. I just want to show you it. I don't care which way you choose. As long as your rate per minute is decreasing, and you got to remember to put that negative there, and your 18 is there. It doesn't matter, okay? So what would I start it at? So let's put a little ordered pair here. When I go to, where does minutes always go? Your X. And P stands for pages. So that ordered pair, M comma P, is big. It's really helpful because it tells me where I put 0. It tells me what I label my axis is. So if I haven't started printing yet, meaning when M is 0, how many pages do I have to print still? 18. So there's your y-intercept. Now I need to find my x-intercept for both of them. So basically, when the pages that I have left to print are 0, what would my minutes be? That's an easy one to figure out. And when my pages left to print is 0 here, how many minutes will that have been? Go, figure that out right now. And it's really just a division problem, right? You guys know that. But to show the algebra behind it. Yeah. I'm just going to do it different ways so you can see that you could cancel out whichever one you wanted. What is this one? 4? No, just 5. Yeah, 5 is good. You guys can't stack more than 4 anyway, can you? Right. All right, let's finish this. All right, so what does this mean? How many minutes does it take me to print my 18-page paper on the laser? 3. How many minutes on the inkjet? 4. How many minutes do I save? 1. What does this look like on a graph? Go. You knew I was going to ask. Yeah, it's like a guess. All right, are we good on this? Okay, pretty easy. All right, let me ask you something else. So we've seen both examples, guys, almost done. We've seen examples of when it starts here, but they're starting at the same point, but your slopes are different. Same y-intercept, increasing. We've seen starting at the same y-intercept with slopes decreasing. And do you understand the relationship between, are you ready? You need to take words, turn them into equations. From those equations, get ordered pairs. From those ordered pairs, graph it. Can you follow that flow? Okay, that is part 1 of application problems.